Well, thank you everybody for coming. What I was hoping to talk about today, uh, in the and we've got some images up on the boards, is some work that I did. Gosh, it goes back to 2014, so the better part of a decade now, was when I first started working on it. And it's funny because these graphs are these charts show graphs, at least the center and the right side one, show we sketched these in the beach at Santa Monica. Myself and Dan and another friend, all those years ago, and then I turned it into a paper and eventually got it published with some resistance. It wasn't well received in a couple of journals that I submitted it to first.
Oh, do tell.
But it did finally get published in Anthropocene. What's that?
Do tell. Why didn't they like it?
Well, the main thing that they didn't like was that I was very critical of the failure of what up until then were the IPCC. So this is the Intergovernmental Panel on Climate Change, the World Scientific Consensus Authority on Climate Science. That intergovernmental body, which is comprised of many hundreds of scientists working together, and then several thousand more as contributors and reviewers. The entire consensus is built around a set of scenarios, and the scenarios for climate change frame the problem. They are something like an Overton window. They provide the context and the definition of the problem and the challenge within which the science can explore possible responses and solutions. So the trouble with those scenarios, however, back then in 2014, when they were when the previous round of scenarios had just been published. These things are done every 5 to 8 years. A new round of scenarios and a new round of climate science publications are put out. The fifth round, is called the fifth climate assessment. That one had just been published in 2014. And this came to my attention through the work that I was doing at UCLA at the time. And I felt that none of those scenarios plausibly depicted what our humanity's actual response to climate change needed to be in order to really get a handle on the problem. And the charts that I included in that paper, the first one, which is over on the left-hand side, is not mine. That's a reproduction of a really quite famous now paper by Pakula and Sokolow. These are climate scientists at Princeton. And this was the picture of what humanity's response to climate change was imagined to be. So all of the major scenarios, 5 major scenarios that framed all of the thinking in the scientific community about how humanity could respond to climate change were framed in the terms of the diagram on the left. And what you'll notice is that the diagram on the left is the y-axis is a rate. So that is the rate of, in that diagram, it's labeled fossil fuel emissions, but you can think of them as just greenhouse gas or carbon emissions, carbon equivalent emissions. And the diagram is a conceptual representation of how to respond to climate change and imagine I'm doing air quotes here, solve climate change. And the framing of it was that that humanity's task was to stop the rate of emissions from increasing. That was the primary framing. And you can see by the timeline that this was imagined to be possible by the mid-2050s, that the humanity's addition of fossil fuels into the atmosphere, that rate is increasing every year, and it has been, and it was long before the year 2000, which is the first date on the first year on the chart. But it has been increasing all throughout that time. And when this original picture was published, Pakula and Sokolow, the two authors, envisioned a conceptual schema a way to think about getting from a steadily increasing rate of emissions to a constant rate of emissions. And they envision doing so through not just one policy measure, but what they described were 7 major categories of effort or undertaking supported by policy in order to each take a wedge out of that the total triangular area that you can see under the curve there. And they called each of those wedges a stabilization wedge, so a climate change stabilization wedge. And the entire collection of 7 wedges is the stabilization triangle. So this is now a key concept taught still in curriculum to environmental students worldwide. The idea that we need to respond to climate change with the stabilization triangle and its constituent wedges. And what I saw here was just a monumental error in my mind, which is that this does not end humanity's emissions. It allows emissions to continue, at least into the 2050s, and then only as a distant thought for the future do we even have the ambition of trying to actively reduce the rate of emissions. And only sometime far out into the future, which is beyond the time frame of the graph. So if you extend the line, perhaps the year 2100, maybe maybe the rate would eventually reach 0. Does that make sense? So it seemed to me that this was not solving the problem. This was only the first portion of a full solution to the climate challenge. And so I use an analogy, and I've used it for many, many years. And that is, imagine your house is on fire. Okay? Imagine your house is on fire. So it's burning, and the flames are emissions. Okay, so that's what the analogy is. So if your house is on fire, what do you do? What is the solution to the problem of your house being on fire? Well, the first step of a solution logically is put the fire out, but not some of it, right? Don't put out half the flames or reduce the rate of burning by 40% or 60% or something. You have to extinguish the fire. Okay, so that would be the equivalent of reducing the rate of emissions to 0. Okay, that at the very least, that is the first step to solving the problem of your house being on fire. But are you done then? No, you're not done. Your house is not. The problem of a house having caught on fire is not resolved until the house is repaired. So once the fire's out, you're not done. You're only part of the way there. You still have to fix the house, and if you're smart, that will include upgrading the house so that add smoke alarms and fire sprinklers or something like that, so that the house can't catch on fire again. But that's the analogy, and so what what that is trying to show is that the prevailing conception of just focusing on reducing the rate of emissions to a constant level, and rather than an increasing amount every year, that is not nearly enough of an ambitious goal to justify or to constitute a solution to climate change. It's at best it's get halfway there. I don't mean literally halfway quantitatively. I mean just in principle. It is only the first step. It's only half of a solution to climate change. A full solution requires not just reaching net zero emissions, which the phrase net zero has become popular since I wrote this paper, not because of me, but just it's entered the conversation now. Net zero, we need to get to net zero rather than ceasing emitting emissions. The ambition has increased, and now the conversation globally is, so we need to get to net zero. But even that is not enough. Even that is not enough. We need to have we need to plunge deep into a regime of what are sometimes called negative emissions, or alternatively carbon withdrawal, and pull carbon out of the atmosphere and oceans in order to repair the damage that we've done to the planet, to the atmosphere and the oceans. And by analogy, that would be the equivalent of repairing the damage that a house on fire caused. And what I argued in my paper is that the evidence at that time about tipping points and uncertainties with climate inertia, so in other words, how long the effects of climate change would last as a result of inertia within these very large and complex systems, the planetary systems, geology and the atmosphere, the oceans, the biosphere, and geological systems, all of them. It's not known to what extent there is inertia in those systems as a result of the forcing of change that we've imposed by adding carbon to that and other greenhouse gases to the atmosphere and the oceans. So that's that, especially at that time, and even still today, there's an enormous amount of uncertainty. So one of the things that seemed to me was that it was the precautionary principle would suggest that we should not assume that the planet will be fine and repair itself if only we reach net zero emissions. That seemed to me to be an extremely dangerous assumption, and that a far more reasonable assumption would be to be conservative and say, well, the only way we can have any real confidence that the planet will not be disrupted by climate change in ways that are harmful to human interests, certainly, would be to restore it to its pre-industrial condition. And it may be that that's not enough. It may be that we might need to go further than that in order to create a reversal of inertia in order to claw back some of the changes that have occurred to some of the planetary systems. So all of this is a way to say that my suspicion at the time, and it continues to be the case, is that climate change is in fact a much, much worse problem than is widely imagined by the public and by policymakers, and perhaps by some fraction of the scientific community as well. That what we have been presented with so far, primarily, has been only part of a full solution. And I have suspicions about some of the psychological and strategic reasons for why the scientific community has not been more forthright about this, because some people are certainly aware of this. But there were no publications, and there were no scenarios that in the climate science discourse that were serious about repairing the atmosphere, not just mitigating the damage that we've done and that we are doing. So that is all sort of context for the thinking behind this paper and the charts that are the charts that are shown here. So maybe let me pause and see if there are any questions, because before I continue talking, does that context make sense?
Does to me. There's a basic planetary physics question. So the amount of CO2 in the atmosphere, you could think of it through very complicated mechanisms perhaps, but fundamentally there are some simple ones as affecting the derivative of the temperature, right? Like if the CO2 stays at a high concentration in the atmosphere, you would expect temperatures to just continue increasing without any, all else being equal, right? It's not, or do you expect that at a given concentration it will reach a certain temperature and stabilize?
The latter, that is correct. The latter is the expectation.
Right.
For any given amount of concentration of carbon dioxide in the atmosphere, you have a certain amount. You have what would be a radiation balance. So an equilibrium between incoming and outgoing radiation. Solar radiation, of course, overwhelmingly a little bit from stars, but overwhelmingly solar radiation coming in, and then overwhelmingly visible light and infrared radiation going out from the planet. And for any given concentration of greenhouse gases, you have a balance there. There's some point at which there's an equilibrium. And we talk about any change in atmospheric concentration of greenhouse gases creates a forcing function, a radiative forcing function, as the planet's mean temperature, shifts towards that, whatever that new equilibrium is. And there is debate about what that is. But even that is a little bit misleading, because the latest climate reports have taken on language that is, I believe it's misleading anyway. The way that I don't want to misconstrue it, but the I don't have a quote, so only paraphrase with the wording. But the wording is that um, research today is showing that if we achieve net zero and stop emitting more greenhouse gases, then the concentration of carbon dioxide and other greenhouse gases in the atmosphere today would only result in a modest amount of additional warming, and that makes it sound like all we need to do is reach net zero, not withdraw carbon from the atmosphere. However, when this language says that the temperature will stop increasing, that is relative to the current
state, yeah.
radiation balance. It is not relative to the pre-industrial radiation balance, and we have already increased the global mean temperature by 1.1 degrees centigrade in the last 250 years, and just that increase has caused I don't have the number off the top of my head, but 15 centimeters of sea level rise or something like 12 centimeters. Anyway, some quantity of sea level rise and a variety of other climate change impacts. And one of the concerns, certainly it's a concern of mine, is that the warming that has already occurred, 1.1 degrees Celsius, even if that were to not increase a whole lot further. So let's imagine we stopped emitting greenhouse gases. The concentration stayed at about 400 parts per million, which is around about what it is today, a little more, 410. And we only say get 1.3 degrees or 1.5 degrees of warming instead of from the historical amount, not from today, not further from today, but relative to the pre-industrial baseline. So that would be about 0.2 or 0.3 or 0.4 degrees further warming from today. In my mind, there is a substantial risk that is still plenty of warming to cause some of the worst climate change impacts because of the inertia in the system and the threat from tipping points. So it may well be that, for example, the collapse of major ice sheets in West Antarctica and Greenland has already been dialed into the system by the amount of warming that has already occurred, for example. That's a distinct possibility. And both of those events would be catastrophic. That would be a very serious problem if those things happen. As I said, this is, it is an area of contention. It's not, there's no consensus on a safe amount of warming in the long term. And I think we are being, as a scientific community, being extremely reckless in failing to admit the potential severity of the problem that we face. And I believe that the reason why that has not been the standard position, why that has seemed like an alarmist position, is because the scientific community has been hesitant to sound alarmist, and has also, I think probably the bigger problem is that the scientific community has not seen a path to a solution like the trajectory I illustrate in the middle diagram there. The scientific community is technologically illiterate, the climate science community anyway. And because of that illiteracy, it seemed unimaginable that we could that there was any pathway to achieving a deep negative emissions or carbon withdrawal regime. That just seemed totally impossible. So if that was totally impossible and unthinkable, well, then we couldn't look to that as a solution. And so then the problem was framed differently, so that a solution seemed so that a more a mediocre solution seemed plausible, which is just getting to net zero. That's my personal take on it, and it was at that time, continues to be today. But of course now, the technological options for getting to net zero and then going into a deep carbon withdrawal regime seem much, much, much more plausible than they did 10 years ago. So this conversation is starting to change, and I'm very pleased to say that the new climate scenarios, the new round of 5 climate scenarios, imperfect as they are, do now include, one of them does anyway, actually 2 of them, do include going into carbon withdrawal regimes later in the second half of this century, so in 2060s, 2070s, 2080s. Now, I still don't think that's enough, but it's the consensus has shifted in that direction, so I'm very pleased to see that. But the
these graphs in Figure 3
yeah,
are still from your original paper, though, right? These aren't from the
yes,
IPCC
no,
report.
those ones in Figure 3 are from my original paper. And so all I was trying to do with Figure 2 and Figure 3 here was illustrate conceptually how to frame our response to this problem. So our house is on fire. We have to put the fire out, and we got a big, once we got to call the fire department. We got to put the fire out. Then once it's out, we don't just walk into the smoldering ruin and kick our feet up on the burnt out couch and say, "Okay, job done. Everything's good." No, then at that point we got to call the contractors and get get all the teams out, repair all the damage that was done, and there's a lot of work to do there. And I was just trying to mark each of these sort of key notable, they're not strictly inflection points on the curve, but conceptually regime changes. So in the center diagram in Figure 2, A is the emissions to date, and that's the regime that we've been in historically. And you can see I was doing it up to 2015, looking prospectively. And then B, the area B on the chart that's the status quo. That's today. We get continued acceleration of the rate of emissions, continued acceleration of the rate. So this, I should be clear, my chart here in the center figure, this is not a rate on the y-axis. This is a cumulative quantity. No, I'm sorry. No, I apologize. I had that completely wrong. That is the rate of emissions. It's the one on the right-hand side that is cumulative. I'm sorry about that. Please scratch that. I don't want to create confusion. I suck. I'm sorry. The chart here on the left-hand side, it is a rate. Okay, so the area B is where that rate is still increasing year after year. We are still accelerating our emissions. The boundary T, I can't read it. T max.
T max.
Is that that is the inflection point at which the rate of growth the acceleration peaks at that time. And that's not a moment. It's not a prediction. You'll notice that these Tmax and so forth, they're not predictions. They are key milestones on the trajectory. And an important milestone will be when the rate of emissions growth peaks. And I hope that we might have already achieved that. It's hard to tell because of COVID, but it's not impossible. But probably we aren't going to achieve, probably realistically, we aren't going to know for sure until later in the 2020s that we had the rate of emissions increase. So the acceleration will have reached its max, its peak, and we'll stop accelerating. Then we will decelerate. And so area C is the deceleration of emissions growth. So we're still emitting more each year. We're just not accelerating the rate of emissions. Then finally, at the T stable, that is this point where where the rate is no longer increasing. The rate is no longer increasing. It is it's steady. So we've reached some steady rate of emissions, but it's not increasing every year. That would correspond to what in the original Pakula and Sokolow chart was, the end of the colored area out in 2055. So Pakula and Sokolow imagined taking 50 years just to stop accelerating the rate of emissions. So we're not talking about net zero, we're just talking about stopping, peaking the rate. Okay, so that's why that's the top of that curve. It's the peak of the curve. Then we enter a regime of declining emissions. And so this is where we are still emitting, but the rate is lower and lower and lower each year. And the current thinking is that this is going to be a very slow and decadal process where it's going to take a very, very long time to go from the peak rate of emissions back down to towards net zero. And what I described in the paper is that I thought that D was going to be fairly brief and driven by technology, and E even briefer, and that we would not asymptotically approach zero emissions, net zero, but rather we would just, shoot past zero emissions, net zero emissions, into a deep carbon withdrawal, all driven by technology, by clean technology to mitigate emissions, and then, of course, facilitated by clean technology, especially clean energy and automation, that we would be able to withdraw very, very large quantities of carbon from the atmosphere and oceans, and that what I wanted to show was that the rate of withdrawal, in principle, facilitated by technology, could at its maximum exceed the rate of the peak rate of emissions. So at some point, and I hope I'm right, this is idealized. And what I hope is that we will throw the whole process into reverse, and we will actually be repairing the atmosphere and oceans, eventually repairing them faster than we were harming them at our peak rate of causing harm. And so this is a way of saying that, hopefully it will take less time to repair the atmosphere than it took to damage, than the 200 years it took to damage it. And so the entire area above zero, net zero on the curve, is mitigation. So when you hear about climate mitigation, that's what it's talking about, mitigating emissions, trying to get to net zero. And what is not part of the global conversation, or really hasn't been at all until very recently, has been what I call in this restoration, that concept. Now, the figure at 3 on the right just shows a few different scenarios where we have to decide what we're optimizing. Are we trying to minimize the area under the curve? Are we trying to get the whole job done as soon as possible? Are we trying to do, the best case scenario where we do both of those really aggressively? Or do we, business as usual, we just continue growing and shoot off the top of the chart? So the figure 3 on the right is a variety of different scenarios for how that could occur. And the chart on the right is, if you want to imagine it, is the cumulative. That is the cumulative, the resulting, I shouldn't say cumulative, I should say the resulting concentration of carbon in the atmosphere. And so what we want there is we want to go from where we are today, which is pretty, around 400 parts per million CO2 in the atmosphere, back down to the pre-industrial level of about 280. And so anyway, that just illustrates some different scenarios of what what we could choose to do, and depending on what we were trying to optimize. Like, are we trying to avoid passing some key threshold? Or, like, if it turns out, okay, well, if 500 parts per million or something like that is a tipping point, and things really go to hell if we let it tip past there, well, we need to be very careful that doesn't happen. And maybe it's more important to prevent exceeding that amount than it is to get the whole job done as soon as possible, to get back down to complete the restoration of the atmosphere to its pre-industrial levels as soon as possible. And so depending on what your criteria are, or depending on if you're trying to avoid thresholds and... Sorry, go ahead.
So one of the trade-offs you might imagine there is the driver of this kind of backwards S-curve that drops down from high emissions to low negative emissions, or high negative emissions, whatever. One of those would be technological development, perhaps driven by, well, if you look at the reason for these renewable energy disruptions you've talked about, part of it is the fact that, well, largely you'd have to think it's to do with China and India industrializing and becoming energy intensive and not accepting the current cost of energy, so that drives down the price due to technological investment. If we restrict technological investment by restricting growth in some way, you could imagine that restricting emissions, perhaps optimistically, in order to avoid some tipping point, but perhaps also ruining this S-curve. Is that the kind of trade-off you maybe have in mind?
Well, yes, that's a scenario, and I think what you would see in that sort of scenario on the right, in figure 3, is you would see something like in that case, the turquoise line, where it limits the total concentration in the atmosphere because you're sort of preventing economic development from occurring. say, for example. But because of that, the lack of economic development might translate into slower technological advancement and less resources to pour into aggressive restoration and carbon withdrawal, and therefore you would extend the time required to actually complete the withdrawal process and get back down to the pre-industrial concentration of carbon in the atmosphere. And so what you would be sacrificing there would be you would be limiting the peak concentration in the atmosphere, the peak acute impact of emissions, but you would be forestalling, you would be delaying the point at which you achieved restoration to pre-industrial levels. And depending on what scientific research shows, which this research has not been done, you would need to decide which of those is more important: to limit the concentration in the atmosphere, or to return the atmosphere to its pre-industrial state as quickly as possible. And we don't know the answer to that question, because this is not part of the framing of the problem, and this research has not been done, at least to my knowledge. Now, all of those different scenarios on the right-hand side, they would correspond to different steepnesses or shapes of this, what you call the backwards S curve. You would still get the general shape of what I call the impact pulse here, which is you would still have the same S curve and then eventually a return. So you'd still have a mitigation phase and a restoration phase, but the steepness of those, the steepness of the curve and the duration of it and so forth. Again, I'm talking about figure 2 here. You would get a different pulse shape that would result in a different concentration curve on the right-hand side. So I didn't show different pulses in figure 2, different scenarios for pulses. I only showed different resulting concentration curves in figure 3. But you can imagine there are 1, 2, 3, 4, 5. No, there are 1, 2, 3, 4 curves, and then the red one isn't. That's just business as usual going to the moon. You can imagine for the 4, where the scenarios where the S1 through what is it? I'm sorry, I can't read S. Why did I label it like that? That seems dumb. I'm sorry. S2, 3, 4, and 5 on the curve. You could imagine each of those having their own corresponding impact pulse. In other words, their own curve of figure 2, their own version of figure 2. But it wouldn't, they would differ somewhat, but not. They would all have a mitigation phase, and they would all have a restoration phase. And so, in other words, I was trying to reframe the entire conversation to say restoration has to be part of the thinking. And then once you admit it into the thinking, then you have important decisions to make, like, should you prioritize minimizing the peak concentration in other words, the maximum extent of the damage, or should you try to minimize the time that the damage is occurring over? So again, switch back to the analogy of a burning house. What should you try to minimize? Sort of the extent of the damage, or how long the damage occurs for? So if you want to maybe extend that, maybe push the analogy a little bit. Imagine your house is burning. Should you try to extinguish the flames should you try to extinguish the flames as quickly as possible, and then not worry about rebuilding the house so fast? Or should you, focus on putting your resources towards the repair work? So you let a little bit more of it burn. Don't worry too much about the maximum amount of burn damage, but then just know that you're going to have to have a bigger repair job. But if you've got committed more resources to repair, you can get the whole repair job done faster. So you can imagine there's some trade-off there. And that was what I was trying to show I guess that analogy doesn't work very well, but that was what I was trying to show in figure 3. Now I hope all of this makes sense. It is nonlinear. It's all sort of unintuitive. You have something like the derivative in figure 2 and something like the integral in figure 3, although the units are slightly different. But what I was hoping to bring to this conversation, in addition to introducing this idea, which is now relevant because the latest climate scenarios has sort of borne out my thinking and back in this paper. But what I was hoping to do was generalize this concept beyond climate change and maybe even beyond environmental problems, to sort of general phenomena, um, social phenomena, economic phenomena, physical phenomena, where you need to escape thinking about things just like figure one, where you just want the rate to peak and then get back to net zero. Where is that not enough? Where else in our lives and our world is that not enough? Where else do we need to think about not just stop doing harm, but also actively repairing and healing, right? So, and I think maybe some of this misunderstanding is, if you forgive me for conjecturing a little for a moment here, but I think some of this may just come out of our own intuitive thinking that's rooted in biology. So our bodies and other organisms and the natural world around us, it has a repair capacity. Our bodies have a natural repair capacity, and ecosystems have repair capacity, and all, so if you do harm to something, then I think our intuition, I think it's not unreasonable to suppose that our intuition may incline us to think, well, as long as you stop doing harm, then things will just go back to normal eventually. They'll just fix themselves. If you stop doing harm, then recovery will happen, healing will happen. And it's happened, that's how it works with us, with our bodies. Maybe that's how it works with a lot of our social issues. Certainly in the rest of the living world, that's how things are, at different scales, and different levels of organization, whether it's species or an entire forest or a whole ecosystem. If there's some source of damage, and then you remove the source of damage, healing seems to be spontaneous. Now maybe it can take a little while, but it's seems to be spontaneous. But with inanimate systems, inanimate objects, things that are designed, things that are engineered, that's not the case, right? If your car gets damaged, if your house gets burned, it is not going to fix itself if you put out the fire, or if it's damaged, it's going to stay damaged unless you fix it, unless you make an active effort to repair it. And so I think that this is this concept of needing to do more than just mitigate, but actually restore. The need to do more than just cease harming, but actually actively heal. I think that is an important general concept, and there is something of a disconnect in our general thinking, certainly about environmental problems. We sort of automatically make the assumption that natural systems will repair themselves if we just stop harming them. And I think that, again, especially with climate change, I think that's an erroneous and extremely dangerous false assumption to make. But I'm interested in how this might generalize to other phenomena. So does anybody have any thoughts of, is there anything else in life or the wider world or the universe where we would expect a pulse phenomena instead of a bell curve phenomena?
I just watched a video on YouTube with my son about the immune system, and when you get a cut or something, that was what the video was about, and you get bacteria inside the wound, it takes sometimes days for the body to marshal all the different elements of the immune system, mostly because there are exponentials involved, right? To fight an exponential, you need another exponential. And so the immune system goes around finding various different components, I forget all the names, but which are targeted to the particular bacteria that you have. And then it starts them multiplying. It sort of wakes them up and they start multiplying. And then when they arrive, if it's sort of scaled correctly, they exponentially destroy the invasion, and it's no fight at all. But I think this deep restoration phase reminds, maybe it's fairly typical of systems that are controlled via exponentials. I don't know that the atmosphere is really like that, though. Maybe our interaction with the atmosphere is kind of like that, given that our economic activity is sort of governed by feedback loops and exponentials. Maybe anytime, it's kind of, unless there's some reason why zero is a lower bound, maybe it's almost impossible for us to really achieve a bell curve, right? Because how do you actually time it so that you really get back to zero? You almost don't fix it or you overshoot somehow and get into deep negative territory.
That's a great point. Yeah, that's a great point. Like, how would you bullseye net zero? I
So
mean, what
maybe
are the chances of actually getting, and even achieving it, like, or sustaining? Like, how
right.
would you sustain where that would and depending on the precision you want to measure things, it's absurd. It's impossible.
Well, it kind
So
of, I mean, getting
yeah,
to zero
that's a good point.
kind of implies some sort of world government and very strict control of emissions, right? If you Because to get to zero kind of means that you're balancing two opposing forces, right? One is something that continually wants to increase it and something that continually wants to decrease it. And that's inherently
Yes.
a situation that's full of conflict. Aiming for zero sort of implies a high level of conflict. Whereas getting deep into negative territory is possible simply because of a fundamental change that doesn't necessarily involve conflict at that level, right? It's just that you've changed the nature of the system and now you just, by its nature, don't have that problem anymore or something like that. It's sort of hard to imagine zero as being a sort of easy way out.
Probably what we would see, what we would expect to see, just thinking to systems dynamics examples where there are feedbacks and there are multiple exponential phenomena are interacting with one another, and they produce variety of different effects. One of which is oscillation around some value, some not necessarily equilibrium, but a stable a stable state of a system will often comprise oscillation around a value or mean or something like that. And we see this in a variety of all sorts of different complex systems. Ecological ones are ones that come to mind, where you can, for example, have the populations of predators and prey. Um, they do tend to grow exponentially and then collapse exponentially, and you can have overshoot, and you can have uh, collapse if you're talking about things like population, which is typically what you would look at with predators and prey. But what we see is that when things settle into a stable system state, a stable configuration, it isn't sort of that suddenly the populations of both the predator and the prey species are constant and unchanging. It's that they oscillate in a stable way around some values. And uh, so I would imagine that at the end of some restoration period, unless you're imagining some more distant technological um, uh, advancements, and at some point in the future that give us a great degree of control over the concentration of the atmosphere, which I suppose is conceivable. Um, it probably is more realistic to expect sort of uh, uh, oscillation around some value as opposed to properly achieving zero. And uh, the natural systems, I mean, the natural levels of carbon dioxide in the atmosphere are like that too. They fluctuate, and they fluctuate around 280 parts per million, or at least they have in the Holocene, in the 600,000 years or so prior, leading up to that. But there have been periods of more sudden change. But there's some sort of for lack of a better word, some sort of stochastic behavior in the system that where there's ups and downs and ups and downs, and basically oscillation, but around some value. And we've obviously, artificially, through burning fossil fuels, we've gone way outside the normal bounds of that fluctuation.
Yeah,
Um,
I think that observation helps in the current climate because it fits with the psychological mechanism, which is that if you aim at zero, you probably won't hit it, but if you aim at negative 500, you might. Uh,
that's a good point too. Yes, 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 yes. Uh, I guess another thing that I suppose I was thinking is that with the if you aim into the negative and you don't hit exactly where you're aiming, well, then you're kind of, at least you're on one of these curves off on figure three, and being on those is better than not being on them at all. And so, I suppose it's aim high is the adage, right? That's the old wisdom, is aim high. Um, and it's the opposite on this graph, but it's the same idea, right? I mean, we should be aiming, and then, like you said, hopefully we'll we may not hit the mark we're aiming at, but at least we'll hit something that's worth hitting, as opposed to missing the target completely, and not achieving what we want to achieve, which is a proper solution to this huge problem.
You may play devil's advocate a bit and say, well, so what? Okay, so suppose nobody thought about restoration. Okay, maybe that made a lot of people, a lot sadder than they might have otherwise been, given the embodied hope in that idea of restoration. But would it have made a difference? I mean, you're sort of asking the question, maybe this was a mistake to not take Adam Dorr more seriously in 2015. And you could ask that question about many other trends, I guess. But what do you... So let's run the thought experiment. If we went back to 2015 and everybody was forced to read your paper and maybe even more difficult, forced to believe it and think it was possible, which seems to me like the major obstacle. I mean, this word geoengineering you have innocuously in figure 2 is like a scary word, or was a scary word. I don't know if it's still a scary word in your discipline.
Yes, that was one reason why I had trouble getting it published. That was a big boogeyman in the climate science and policy journal that I originally submitted to.
Right.
That's exactly. You put your finger right on it.
Yeah, I could. Not surprised. Okay, so suppose you magically cured that back in 2015. Well, what would have been different? Would anything have been different? It's not. It's not so clear that.
I mean, there's perhaps some question technologically of to what extent there's the trajectory of climate mitigation and then eventually restoration is inevitable as a function of technological advancement, and what would we really have done anything different, taken any different steps? Would we really have accelerated the entire pulse trajectory, brought the peak emissions date closer, brought the net zero time closer, brought the negative, the restoration regime closer? Would that really have happened if we'd been serious about it? Or would this just have frightened and panicked and concerned people and alarmed people and depressed them and made them pessimistic and even more than they already are about the prospect of the future and solving things and would I think it's a perfectly fair question. Psychologically and socially, would it have made any difference, and might it have caused harm to believe that to see the problem for perhaps, if I'm right, what it really is, which is worse than we were led to believe by policymakers in the scientific community? And I suppose that's a good question.
Yeah, I guess
that wasn't made any difference.
Wasn't quite my question. I suppose I'm too much of a stubborn classical liberal to think that scientists should do anything other than tell the whole truth as they know it, and I think it's fairly disgusting when people...
That's absolutely an opinion of mine, 100%. I don't know, sorry to interrupt you, Dan, but you may have seen a recent publication of mine. Sorry, just indulge me a very quick story. I wrote a follow-up paper to this at the invitation of a major climate journal. They invited me to write an opinion piece, and I wrote the opinion piece. And then when it went to review, it was too radioactive, and the editors liked the piece, but they said, "We're really sorry if we can't publish it."
Oh, I remember that. You sent it to me at the time. Yeah.
Yeah, and one of the major things that I concluded the paper with exactly the point you just made, which is that our responsibility as a scientific community is to the truth, not to trying to manage public perception for social engineering purposes to, maintain whether it's contain panic and concern or maintain alarmism to keep people motivated, to minimize climate complacency around climate. If people think there's a technological solution, they'll stop worrying about trying to change their personal lifestyle habits, which is the major prescription right now, is to fix this problem with lifestyle change. The reviewers were full of all of the reviewers that I had who were concerned for precisely those reasons. If we tell the whole truth, what you're saying gets out there, and we publish this in this journal, it's gonna make our jobs harder of doing the social engineering. And I couldn't believe it, and that's where I ran into real trouble, and that's what ended up being so controversial. Is I basically told the reviewers to get fucked, and the truth is what mattered, and they. And then the journals said, "I'm sorry, we can't publish this. It's too controversial."
Well,
but I didn't, anyway. So I'm 100% with you, Dan. That our job as scientists is the truth and the whole truth and nothing but the truth, and that's it basically. It's not up for us to decide what is safe for the public to know.
We only have a few minutes left. We can continue this next week, I guess would make sense.
Sure. I mean, again, as I said a few minutes ago, I mean, again, really, my goal here was not to sort of, wag my finger or gloat or anything like that.
Sure,
I'm very
sure.
pleased that the climate science community has come around to seeing things a little bit more my way, and I think they will continue to do so in the future. But mostly, I'm optimistic about that, because I think the main reason for that change is not some sort of sudden realization that the problem is worse than we thought. There's maybe a little bit of that, but I think more likely the explanation is that solutions seem more plausible than we originally believed, because the state of technology is advancing, and our understanding of technological progress and disruption, the work that I'm doing and others are doing, is making a plausible pathway for actually going into a restoration regime, is making that clearer. It's making that seem less like science fiction and more like a real possibility that we could achieve and we could afford, and that civilization can start to get excited and be optimistic about that. And I think that that's fantastic. What I do hope, though, maybe we can talk about this next time, is I do think this is an important phenomenon as a general pattern. The idea of a pulse of impact, a pulse of harm followed by a repair. So I guess the whole pattern is like a heartbeat. It's like a pulse, and then you have some surge of harm, and then an equally strong surge of repair. And I would like to see if there are other ways, other environmental issues, certainly, because of course that's my focus, but elsewhere in the natural world, but in medicine and biology and elsewhere, where the same pattern, the same phenomena applies, and where we might draw insight from that. How can that inform our thinking on other topics, social topics, economic topics? I think if we look, we will probably find this pattern elsewhere, and it may be interesting.
The crux seems to me. So I'll tell before I get the general point. I'll give another example. So I follow Sam Altman on Twitter. Sam Altman is the CEO of OpenAI. He's a kind of well-known.
Yes. Yeah.
Ran Y Combinator for a while. Well-known figure in Silicon Valley circles. So he's often saying things like, "We should start thinking about what to do with all the wealth we're going to have soon." He's referring to what he thinks is coming with regards to disruption in artificial intelligence, and partly people are very scathing about that. At least some subset of the community. There's people that are just always upset at anybody who runs a company for various reasons, especially a rich person in Silicon Valley or in San Francisco, where there's homelessness epidemic and many other problems, and to see a rich person sitting there talking about how much cake everybody will be able to eat soon seems offensive to the nth degree.
Yes.
However, I think he's right.
Probably right.
And it's a very interesting problem how to get people to see that. So I think it's not dissimilar to the problem you had with this paper, perhaps, because, well, you don't work in the fossil fuel industry, but you could, right? Suppose you were working in a think tank in the fossil fuel industry and you wrote this paper. Well, it would seem extremely self-serving, right? It's kind of like you're saying, who cares about part C? Let's emit whatever we like because D, E, and F are coming, and whatever, we'll be fine.
Yes, that's a very good point. Yeah.
However, the people, in many issues, say with Sam Altman's case, there are very few people in a position to confidently predict F, especially if the technology required to make F look plausible comes from exactly the same technology or circle of technology that is making C, D, and E possible, right? So
Yeah.
it happens to be that removing carbon from the atmosphere is a very, very different problem to refining petroleum, at least as far as I understand it. So there isn't so much overlap, but in many disciplines there is, and AI is one of them, right? It takes the same forces that are making our social fabric disintegrate from Twitter and Facebook, and have all sorts of problems with surveillance capitalism and many other things we're concerned about. The same engineering technology required to make that work is what's going to unleash potentially a great wave of abundance from automation. So the same people who were in a position to predict
I think you're more right about the fossil fuel industry than maybe you realize. One of the not the only one, maybe not the best one, but a major form of carbon withdrawal is to capture the carbon dioxide from the atmosphere and then pump it back down into old oil and gas wells. And you can guess exactly who the people are with the expertise that's going to be required to pump billions of tons of CO2 back into the ground back to where it came from in the first place. It's going to be the same industry, or either reform, but certainly the same expertise and skill sets, and probably a lot of the same individual people. So I think you're absolutely right, and more right than you even realized, because the fossil fuel industry, or the remnants of it, will be involved in sequestering carbon dioxide that is captured. Absolutely.
Okay, maybe that's a good place to stop. I got to head off to the next session. But thanks a lot, Adam. That was great, and we'll pick it up next week.
Let's pick this up again next week. Thank you, Dan. This is really, really interesting.
Great. Thanks everyone for attending, including the newcomers here. I hope to see you next week, and I'll catch you all later.